but I want to complain bitterly. I don't know what I've done to them to make me talk after David Landau. This is ridiculous, you know, so I want you to know this is not an easy task. But anyway, I love to thank the organizers, especially Paulo Martin and David Landau, for inviting me to such beautiful place and such beautiful conference. There's a shift in the talk to non-equilibrium phenomena. So you've been listening to equilibrium statistical physics, so now I'm going to talk about non-equilibrium phenomena, but perhaps the simplest kind of non-equilibrium phenomena. But the title is a little bit strange, so let me start by saying a few words about the title. And before I begin, let me also thank my collaborators. Jacques Amar, who's now professor at University of Toledo, was my postdoc for some time. We worked on this. And Mikhail Popescu, who's now a research director in Max Planck Institute Stuttgart, was my graduate student who also worked a lot of problems on surface physics. So what is this title about? I will tell you about thin film growth, what it is, and what does surface roughening in thin film growth means, and what is the problem that I'm going to talk about from a physics point of view. But I also have this beginning part, a golden lesson from nature. It's just that I couldn't avoid thinking how wonderful this particular problem was and what it teaches us. So I added another non-physics, if you will, dimension to my talk, which I hope you enjoy. What I'm going to do, the reason is, basically, what I'm going to do is to talk about a problem where there was a real contradiction between theory and experiment. Once a theory is established in physics, it should apply to everything. It shouldn't change once you get a new experiment. And so when something like this happens, it usually is called a paradox. These are, again, the kind of paradoxes that you've seen before. The most famous ones are like black body radiation, photoelectric effect, relativity itself, where we knew the physics perfectly well. You know, the physics is well established, but all of a sudden you get experimental results that contradict with this almost common sense phenomena. And this is really valuable. So I wanted to bring out that aspect of it too. That's like a dessert in this talk. But let's start with the talk. The talk is about thin film growth. Let me start with thin film growth. What is thin film growth? Thin film growth is deposition of atoms on a surface. And it can be done in a wide variety of ways. You just gently or in a very fast way, you add atoms to what is called the substrate. This surface is called the substrate. There are many ways of doing this. The particular technique that I will talk about today is molecular beam epitaxy. It's just one of many different techniques, and it's perhaps the simplest type of process to think about in terms of thin film growth. So here's a very nice view of a simulation of earlier stages of thin film growth. You start generally with a clean substrate on which you deposit materials. These materials form aggregates, and they grow into little islands. And these islands then eventually connect to each other and percolate and form a layer. So I think I have the same problem as David. So the first question is, why do we care about thin film growth? Well, it turns out that thin film growth is really one of the most powerful ways of making designer materials. It's a non-equilibrium process where by tweaking the parameters in the system, you can create wide variety of materials for many applications in in terms of optical properties, electrical properties, chemical properties, mechanical properties. And then you ask your question, all right, so what is the use of these thin films, it turns out that none of the modern technology would have existed without these fancy thin film growth materials. Anything from internet, cell phones, and computers, it owes itself to development of these special types of thin films. But I'm not an engineer, so that is really not the real motivation, for me at least, behind doing this. As I mentioned to you, the real motivation is the fact that thin film growth can be thought of as one of the simplest non-equilibrium phenomena you can think of. And it's a very challenging problem because we really don't have a theory or a simple model of non-equilibrium growth. And so looking at this problem of thin film growth, not only you're going to contribute to understanding something that is technologically important nowadays, but also try, hopefully, understand a little bit about non-equilibrium processes in physics. I guess you have to go close. No, not yet. All right. Let's go back to what type of thin film growth process I'm going to talk about. I'm going to talk about molecular beam epitaxy. Molecular beam epitaxy is a method for making one of the purest types of crystals there is. In this technique, which you do under ultra-high vacuum, you have a substrate in a chamber that is highly evacuated, to which you send material to be deposited. And what is important from a technological point of view is that you can send in almost any kind of material, any type of atoms onto this substrate. From these cells, which are called effusion cells, the material is heated here, and they sort of gently just go and get deposited into the substrate. In addition to making this very pure form of crystal growth, you also have a lot of control on the process in the sense that you can put different types of materials in different effusion cells and stop one kind of deposition and then deposit another type of atom in it. So bury one type of atom under another layer of type of atom, and so on. And in addition, you have a variety of analytic tools, surface analytic tools, like Reed and Lehm and so on, to analyze the surface morphology. So what do you get? All right. So what do you get? Well, in the earliest stages, you get atomic deposition. So this is really a question of what do you get as a function of time. So here is the length scale of what you get, and here is the function of time. And if you deposit for very short time, you're just going to get some atomistic structures that you have to study generally with like density functional or some very detailed quantum techniques. But as time goes on, you deposit more, you get larger structures and larger structures, and so the technique that you can use to study it changes. If they're sort of mesoscopic, you probably would use molecular dynamics, or microscopic is still, you use molecular dynamics. But as the structures get larger, you can start using Monte Carlo techniques, and then eventually, when the system is very large, you can approximate it with some kind of a continuum equation. From practical point of view and from physics point of view, we really are generally in this kind of range of a scale and time. We want to see what happens to the system when several layers are deposited, and that takes seconds. And also, we want to see a structure, not individual atoms, not from chemistry point of view, but more from physics point of view. And so both Monte Carlo techniques and continuum equations are really the most useful tools for the study of surface properties at the times and length scales that are relevant for physics, for understanding the physics of the problem. So you will see that the key to understanding these thin films is understanding the surface evolution, how the surface evolves with time, and also the structure of the surface, the morphology of the surface. What do I mean by surface morphology? Well, surface morphology is the shape of the surface at any given time. Here is the picture that I showed you before. So at very early stages, there is nothing on the surface is flat. Later on, the surface becomes rougher and rougher. And here is the slice through the surface. So this is the direction of the growth is changed here. So this is early stages of the growth. And as you deposit material, if you look at the surface, it is changing. So this is called surface morphology. And what is important is that surface morphology is a dynamic phenomenon. It's an evolving surface that we are interested in. So how do we study something like this? Let me show you results of some, don't worry about what kind of material this is, but some kind of an experiment where we could look at the surface morphology as a function of time. This is earlier stages of the growth, and this is the roughness of the surface. Think about it as the distance between the peaks and valleys in the surface. That's the easiest way. Or the root mean square of this roughness there. So early on is pretty smooth. It gets rougher and rougher and rougher as a function of time. And you can see more and more features are growing on the surface as a function of time. So this simple picture shows us three things. One is that surfaces have a random fluctuating structure. The reason for it is that the deposition process is random. As atoms come down, they land randomly on the surface. So you certainly will have a random structure. And the surface roughness looks like a very nice quantity to characterize the evolution of the morphology. All right? So surface roughness here is not significant, but as time goes on, the surface roughness becomes, larger and larger. And what it shows is that the surface roughness grows with time. So these three features of surface roughness, surface morphology, are useful perhaps for characterizing them. Again. All right. This is a picture from Blue Ridge Mountains, but you can look out here also many places. In Brazil, you know that when you are far away from a surface, it doesn't look very rough. This looks almost like a flat surface, even though these are very similar mountains. Like here, this maximum roughness is just a few centimeters, right, on this screen. But look at this roughness. This is almost, almost a meter, the same thing that would appear just less than a centimeter there, it appears like a meter. And so surface roughness depends on the scale, depends on how far you are from the surface, how you look at the surface. So overall, we have three observations. I want to repeat them again because they're important. That roughness is a good measure of surface morphology. You look at these surfaces, that's not bad to say that this has a certain roughness, this is a different roughness. In thin film growth, and of course in any kind of surface, roughness depends on the scale of observation. But most importantly in thin film growth, because we are interested in evolution of the morphology, we notice that surface roughness grows with time. That's what we saw in the STM experiment. So how can we combine these two? Well, I'll give you just a brief overview of the scaling idea of surfaces. So in this idea, you take a rough surface and you say, okay, what do I know about this? Well, what I know about this surface already is that it has a characteristic roughness, which you can denote it by the width of this surface any way you like. The distance from the top to the bottom, or root mean square of the fluctuations, give you a measure of the roughness. But in addition, there's another important length in the problem. The length over which you observe the system. As we said, surface roughness depends on this length as well. If this L was very small, here you would have very little roughness. But if the length is large, you see the roughness is this much from the peak to the bottom. So this is as relevant as the vertical the distance W. This is the horizontal distance L. Well, the thing we can do is to say that perhaps from a statistical mechanics point of view, from a physics point of view, this width represents some kind of correlations that exist between different parts of this evolving surface. You have a surface that's evolving, and the way this roughness is generated is through the correlations between the different parts of this surface in this direction of the growth, vertical growth. In addition, if you concentrate on any feature on the surface, right, as a function of time, it doesn't stay steady. It's not a static problem. It's a dynamic problem. So these features evolve, and what they do is they spread with time. And how they spread can be thought of as the spreading of correlations, just like, you know, the Ising model that David was talking about. There's a correlation length. Here, xi parallel is some kind of correlation length between different parts of the surface along the surface, whereas xi perpendicular gives you correlations perpendicular to the surface. So we have two correlation lengths. So the dynamic scaling idea is the following. It's very simple. It says, look, these two are generally independent and depend on the dynamics of the system. But there is no characteristic time or scale that characterizes them, so that we would expect, going back to, again, to the idea of critical phenomena that David was talking about, we would expect these correlations to grow as power laws. The reason these exponents are you know, denoted strangely is historical, but think of this just as one exponent and beta as another exponent. Beta characterizes what I've been emphasizing, the fact that the roughness grows with time. So beta characterizes the growth of the surface roughness with time, and this 1 over z characterizes how features on the surface spread along the surface. And because after some time the surface evolves according to what is your length scale of observation, these two ideas can be combined into a dynamic scaling form, in a sense that the width grows with this exponent alpha, which is z times beta, times some universal scaling function that has a very specific property. This universal function has to grow at x to the beta for a small x, and at long times it reaches a constant because the system evolves into length L. Well, just for historical reasons, like David was showing from 92 years ago, this almost feels like 92 years ago, but this is the original simulation in our paper from 1984. This is the largest system size we could do in one dimension, basically 1 + 1 dimension simulation of ballistic deposition, in which I'm plotting the scaling function. So this is W times L to the minus alpha. The values of alpha and beta don't matter really. Don't worry about those. But you can see that the data did show a very nice collapse with two different values of the exponent, validating the fact that you really in thin film growth have two length scales. You know, until then, the idea was that carried over from Ising model was that people were analyzing them with one correlation length. Nobody thought there could be two correlation lengths, and that was the main contribution here. That actually there are two correlation lengths in this problem, initially f of x grows with the exponent beta as a function of x, and then it saturates like that. Okay, so this is the idea of dynamic scaling that one can use to analyze surface morphology. This idea, since 1984, has been applied to thousands and thousands of different problems, both experimental, theoretical, simulational, and generally it's been an accepted theory, and it has worked in most of the cases, and had been working. But now let's look at what happened in MBE growth, in thin film growth. In thin film growth, or MBE growth, the processes are very simple. What you have is deposition of atoms, mainly, onto a perfectly cut crystal. Imagine you have cut a crystal at 100 or 111 or some surface. You're depositing atoms gently on the surface. For the purpose of this talk, think about what we call a homoepitaxial growth, deposition of same atom on the same substrate. Copper on copper, gold on gold, iron on iron, some very simple, metallic system, if you like. So what happens is that atoms gently land on the surface, they diffuse, and once they become nearest neighbor, there's some kind of a binding, extra binding of the atoms that freezes them into an island. Sometimes atoms can diffuse along the edges and so on. But basically, the main process is deposition of atoms and then diffusion of the atoms on the surface and aggregation of these islands. Here's the Monte Carlo simulation. Is different from the equilibrium simulation in a sense that you don't have the detailed balance that you have there, and the probabilities of moves are dependent on the initial and final conditions rather than the kind of metropolis algorithm that David was talking about. So in a basic simulation, what you do is you deposit atoms onto a substrate, and here are different simulations. What's the difference between them is the speed of deposition. If the deposition rate is very high, the atoms don't have that much time to move around, so they make a very fractal islands. They freeze almost as soon as they hit another island. But if the deposition rate is slower, there is time for atoms to diffuse, and so you make a more compact islands. These white atoms are already depositioned into second layer, third layer, and so on. So you can imagine these three-dimensional islands are forming. This is another talk, of properties of these islands. They're very useful in the experimental realm in a sense that they can be used as quantum dots because electrical and optical properties of these islands are very different than the bulk property, and you can freeze them, but as I said, by depositing another type of atom on top of them and using these thin films for particular purposes. But this is not really the purpose of my talk. The purpose of my talk is to talk about what happens when you deposit many, many layers. I want to talk about evolution of morphology when many layers are deposited. So what happens? Well, very simple. You get peaks and valleys. These dark areas are valleys. Very light areas are peaks. And so you get an evolving surface that consists of the little mountains and larger mountains that spread and grow with time. This is not that different from what you find in a randomly rough surface, randomly rough function. If you look at the mathematical structure of these surfaces with things like structure factor that you would measure in elastic neutron scattering or read, electron diffraction, what you find is that neither of these functions or any other quantity that you like that you measure is a measure of the morphology. There's no characteristic length. This is k, so it's related. The wave vector is related to the wavelength of observation, and there is no characteristic length. There's always some kind of a decay which is related to the surface fractal roughness of the surface, which you might be familiar with. So these surfaces are basically self-affine fractals, and the slope of these things are that exponent alpha, and this was very well defined. So what happens when you do experiments in MBE growth? Well, nothing like that is found. So I already talked about that. So, but experiments don't find anything like this. nature basically does not agree with what we thought made a lot of sense, right? So there were many simulations, there were a lot of theoretical work done on this problem, and all of them thought that the important thing was to measure the exponents, alpha, beta, and z, and try to come up with better simulations or better, theoretical ways of calculating those exponents. But when the experiments were done, what was found is that, lo and behold, there is a characteristic size in every one of the experiments that people did. This is rhodium on rhodium, work with Sui at UNC Chapel Hill. This is tin. This is germanium and germanium stuff done at University of Michigan. And iron by iron work was done at NIST by Strasio. And a very nice looking one, which tells you what happens, is the work of Wendell Kern at Oak Ridge. This is copper on copper. And you can see in this picture beautifully that the system evolves into these little hills, that grow. This is 8 layers. This is 21 layers. This is 73 layers, 115 layers. So what's happening is that you have terraces, islands that run into each other. They grow, and they grow, and they grow as you deposit more and more atoms. So the main question, of course, is what is this? Where does this instability comes from to formation of these mounds? These mounds are reminiscent of equilibrium facets, right? You know that under equilibrium conditions, crystals have a surface facet, faceted surface. These facets are 1,0, 1,11, those kind of facets that people study in equilibrium crystals. But here, what we observe are facets, but these are non-equilibrium facets. So we don't really understand how can you have, there is a balance in formation of a particular facet. That's why they form, is that there's a balance between addition and, desorption. There's a detailed balance in non-equilibrium crystals, in equilibrium crystals, and that's why you get the facets. But where does that come from? Because these are actually facets, but they are non-equilibrium facets. And as I will show you from the experimental results, the structure of these facets is very different from equilibrium facets in the sense that these are 115, 116, 126, or something like that. Nothing that is observed in equilibrium phenomena. So they are unrelated to equilibrium phenomena. All right, to make the story short, it turns out that one thing that none of the theories or simulations included was a tiny effect that had been known for a little while. Namely, that there is a small asymmetry in the potential near the step edge. As an atom approaches in the step edge, the activation barrier all along this step is EA, but as it approaches the edge, all of a sudden there's an additional step barrier in going down the step. So what that means is that if you calculate the probability for an atom to diffuse down a step or go back, there's a higher probability for the atom to go back on that terrace. This is a very small energy, like 0.03 electron volt compared to 0.3 electron, hundreds of times, maybe tens of times or hundreds of times smaller than the original activation energy. This was observed experimentally by Garrett Ehrlich at Illinois. I don't know if you ever knew about him. He was a giant in surface physics. He worked on atomic emission microscopes where he calculated a lot of the initial calculations. He did a lot of initial calculations of diffusion constants of atoms on various surfaces and tungstens and things. And also this was found by Schwabel in a density functional calculation, because he realized that there was slight difference in going down a step or up the step for an atom, somehow the distance at some point is larger once the atom is going down the step. But that's not so important. But the main point is, how does this small effect, namely the Ehrlich-Schobel barrier, cause the mound formation? To do this, let's go back to the kinetic Monte Carlo. Much of the work done on the surface growth in simulations had been on solid models. I don't want to go through the whole history of these problems, but solid models are models in which, when one considers the position of atoms, atoms are deposited on top of one another. That's why it's called a solid on solid. Whereas in reality, if you want to include the step barrier, what you have to do is remember that when atoms are deposited, they form a surface like this, where there is a 4/4 hollow where an atoms can sit. And atoms cannot really sit on top of another atom. They move, they diffuse. Once the atoms diffuse, they diffuse into a 4/4 hollow. So the simulation had to be done by looking at a realistic surface. So what we did was we looked at this O1 surface. So there are both 4/4 hollows, and there are atoms that are sitting in a layer below. And to model this diffusion, atoms can go from one, they can hop from one 4/4 hollow to another one. And if an atom is sitting at the step edge, it goes from the upper layer, 4/4 hollow, kind of incomplete 4/4 hollow, to another 4/4 hollow point in the lower level. The maximum facet you can have is a 1-1-1 facet in this kind of structure. And so you can do the Monte Carlo simulation with this kind of more realistic structure. And when you introduce the barrier, instead of finding the result that I showed you before, namely a self-affine fractal, what you find are actually these mounds. So mounds do appear once you introduce the step barrier in the Monte Carlo simulation. We did variety of simulations with different parameters, as well as the speed of deposition, which you can also think about it as the temperature of the substrate. High temperature substrate or low temperature substrate produces the same effect as fast deposition, slow deposition. And in all cases, what you observe is the formation of these islands or these mounds. This is after just 100 layers. So how do you analyze this surface morphology, this island morphology? Because it's a little bit different from what I showed you before, but the same idea of dynamic scaling applies to this as well, with a slight change. The change is that now we have something else that is evolving, namely the width of one of these mounds. So if you think of these mounds as something looking like a triangle, the height of these mounds is the width that I was talking about before, and the width of the mound is a length r. Both of these now grow with time, and this is nothing but the parallel correlation length, so it has an exponent of 1 over z, and because here they're running to each other and coarsen, borrowing the language of equilibrium, coarsening problems, you can call the exponents. The literature, switches back and forth, so I give you both, that you can call this thing n. In the experiments, I will show you the experimental data, but you can see from the pictures that what you are seeing during mound formation is not that you have mountains that are getting steeper and steeper. What you're finding is that these mounds run into one another and they coarsen with time. Their sizes get larger, but the angle is fixed. So this angle, whose tangent is just W over R roughly, right, is constant. what it implies already, if you assume that this angle is fixed, like a particular surface, the plane is selected, is that these exponents must be similar. Beta must be equal to n in order for W over R to be constant with time. And so I'll show you the experimental results. There are a variety of experimental results, and this one is particularly from Sui's experiment on rhodium. This is a nice plot because it shows the ratio of the width to the length. So this is proportional to the angle. And what you observe is that, sure enough, after just a few layers, the angle stays constant. So these mounds are growing, but the step is selected. The plane is selected. The angle is selected already. And the coarsening exponent is roughly about a quarter in this experiment. I'll show you another one. This is, I think, iron and iron. Yeah, this is the iron and iron experiment of Astrosio. The width grows roughly at 0.25. This is W squared, so this is not 0.25. This is a half, but beta is about a half. N is about a quarter. N is about a quarter. And again, the angle, you can see, is selected after a few layers. In this particular experiment, which I will concentrate on, because the particular value of the angle depends on what material you're depositing. So while the exponents are universal, beta and n could be similar, about a quarter, this angle will be different depending on the microscopic properties of the system. For iron, W over R is about 0.07, tangent of which, you know, is a tangent of about 13 degrees. So think about, you know, this number from iron experiment. So how about theory? So what happened to the theory? Well, I will say a few words about the theory and just leave it. Much of the theoretical work in this field has been done with Langevin equations, because you see from the physics of this problem that surface evolution involves roughening and a smoothing at the same time. Because if the system was just rough, you would see a Poisson rough surface after a long time. So there must be some smoothing processes as well. And these smoothing processes will depend, of course, on properties of the surface, right? I mean, different parts of the surface are smoothing at different rates because of the way atoms move on top of them. So how do we study like this kind of system? Well, we already said that the system has scaling properties. So one of the best ways to look at a system like this is to use a Landau approach. Landau says that if you have a system that has scaling properties, when you write down a theory, you have to write down all terms of the same magnitude, because they have to scale the same way. And so if, for example, you look at evolution of the surface, if I call the surface h of x of t, right? When I look at how the surface evolves with time, I have to write down a balance between smoothing and roughening processes. So the roughening process in thin film growth is the noise that comes from deposition. Deposition is random, so we have a random noise due to deposition. That roughens the surface. What is the smoothing term? The smoothing depends on properties of the surface. How big the surface the slope is. If the slope is large, you deposit atoms, they go down faster, they won't stick to the side. If it's smoother, the atoms stick. And so it depends on all these parameters. So which one of these are we going to keep? As Landau said, you got to keep, you got to write down all of the terms. You got to write down all of the terms, and then choose all the ones that have roughly the same magnitude, because they will scale in terms of scaling, because they will balance each other and give you the evolving surface. So in this particular problem, I won't go that much more into this. If you have surface deposition and surface diffusion, you have a current on the surface which defines gradient of a chemical potential, which is related to the surface morphology. Basically, it gives you a term of order del to the 4. Okay, this has to be negative, otherwise it will blow up. I mean, it is a negative sign there. And so the terms that you will have in the 4th order are like this, but if you think just this one is the dominant one, you get a number for the exponents. Just this is just to give you a conceptual way of thinking about the surface roughening, gives you numbers that beta and n are roughly about a quarter, and that exponent z is about a 4. So Langevin equation with a bunch of assumptions does give you an idea about the exponent. But what about the main phenomena, which is angle selection? There is no microscopic or any kind of theory for that. So what we did was we looked at the simulations, and we see the same kind of behavior in the angle, that eventually the angle does saturate, but this is, I can explain this, but it's not important. But this region shows that actually you do have faceting, as you saw it in the picture, and the exponent beta and n do agree with the value of about a quarter. Just to show you the unphysical nature of solid-on-solid models, you can see that if we had looked at the solid-on-solid models with a step barrier, the surface would have blown up and they would have grown exponentially, which would be unphysical. All right, so this is just the discussion of the exponents. I think we can calculate them, we can understand the coarsening and so on. But what about the mounds? That's really the main question. So what selects the mound angle? To do that, we introduced the following concept. We said, think about what happens when you deposit the atoms. When you deposit the atoms, you're producing 2 types of current of atoms on the surface. One type of current is current of atoms going down the steps, and another kind of currents are atoms that are going up the steps because of the Schwabe barrier. Okay? The introduction of the Schwabe barrier says that there is a higher probability for atoms to be reflected from the step edge and go this way than go down. So what will happen to this atom is that once this atom goes back, another atom is deposited, they will stick and give rise to a current of atoms that go up the hill. What are the downhill currents? Downhill currents come from atoms being deposited at the step edge. So if you have a very high, very steep surface, there's a high downward current because atoms are deposited all the time at the step edges and they go down. If the surface is flatter, the atoms are reflected back and you have a higher upward current. It is the balance of these currents that selects the mound angle. And we can calculate that both in the simulations and in a simple random walk model. So I won't go through too much of the discussion. Basically, as I said, the downward current depends on the slope m. M is the slope. The higher the slope, the higher the downward current, which is negative. The upward current is a little bit more difficult to calculate, but initially it's proportional to the slope. It increases and then it decreases. And it is the sum of these two slopes, these two currents, that selects the slope. When these two currents add up equal to 0, you get the slope. For particular case of the iron on iron, we find the value about a quarter, for the slope about a quarter, which means the angle is about 14, in agreement with what we saw in the experiments. So to show you that, here's our final results from the simulations. Are the dotted, the symbols in this picture, and the dash curve are the expressions that I showed you for the current. This is the total current on the surface. Initially, when the slope is small, the current increases, and as the slope gets bigger and bigger, the downward current increases, and eventually, if the slope is high enough, you have a negative downward current. And where they balance, the total current is 0, is when the angle is selected. The difference between the two curves is the following, is a little detail, but it's interesting to talk about it. That in one simulation, there is, atoms are deposited, and if they're at the step edge, they go down. That's it. There's nothing extra put in. But in the other simulation, what we have put in is some kind of a transient kinetic, some kind of funneling effect, meaning that there is some residual kinetic energy that when an atom reaches the surface, maybe it can continue go down one step, one layer or something like that. So instead of just stopping where it lands, it could move another layer down. There isn't much difference between the two, and the selected angle is very nicely in agreement with what you see in experiments. So I have minus 3 seconds. So I conclude. There's no major conclusion except to say that this was a really wonderful lesson from nature, something that we were all comfortable with, we had thought we understand and so on, all of a sudden was thrown out by these beautiful experiments, all coming out roughly at the same time. And it was interesting that the resolution of it also came from the left field, from something extremely microscopic. We wouldn't have thought of that. Nobody would have started looking at surface growth by putting in Ehrlich-Schobel barrier, even though some people, knew about it. So sometimes progress in science occurs in a different way, rather than doing, something better and better. But sometimes you have to do something very, very different from what you did before. So I hope that's also a nice lesson from this picture. Thank you.